Right, the aim of today's presentation is to look at meters and various tools for making measurements. Starts from things that are very simple, very cheap, to something that's a bit more complex and obviously a bit more expensive. But before we got to the tools, we thought we ought to raise the question of safety on the workbench. And there's a few tools we could use this for that. If you go to a tool station and you pay a whole £1, or you can get a mains tester. Most of you probably have one of these. You put your finger on the cap at the end and you touch anything that's live, the neon inside the screwdriver lights up. The problem with that, potentially, even although you can see it's insulation down the shaft, when you're prodding inside mains instruments, you might not want to have an actual contact between you and anything that's live. So another potential instrument then would be a volt stick. As you can see at the end, it's all plastic, so there's no contact between the instrument and any live wires inside a power supply or a controller, whatever you're using. So there's no danger of you poking around in there and doing shots and so on. So to show it quickly working, I'll just switch to the desk view. Right, there's a power supply. There's the volt stick. The volt stick is powered. It's got a AAA battery to make it work. Look, if you see it, it lights up in the presence of live. Nothing on the neutral, lights up in the live. So you could test not just the outlets. For example, you can test the cable. If it lights up, the cable itself is live. So that's the volt stick. There's another one of chicks. Same idea, only more sensitive. So you can see it's audible and it flashes quite brightly in the presence of a mains voltage. But it doesn't differentiate between the live and the neutral of the earth. It just knows in that area. So if we're working with, here's just an AC transformer in a box, 2 mains in and 2 18 volts AC out. And it knows it's live. It knows that the cable is live. Oops. What you don't know, though, is the chassis live? So this is good for doing the basic testing, but you might want to follow up just to confirm by touching the metal parts. The neon doesn't light up. So it's mains inside, but there's nothing on the outside that's dangerous. That's testing for a live wire, but you might want to even check that your sockets you've got in your garage or your loft or whatever are correctly wired, especially if you've had a cowboy in to do them. So you can buy these socket testers. You can see there's lights along the top, and you can check which ones illuminate, and it'll tell you what's correct, what's incorrect. Right, so we can use the outlet tester just to check whether there's no leakage between the live and the neutral or whatever that might go back and damage your equipment. And the last thing to test before you start fault finding is using the infrared thermometer. There we go. You can see that.
Put that in there, shine the laser on there. That prints at 40 degrees, 42 degrees. And this print is at 18 degrees. Degrees, 65 degrees. What you're not seeing is there's a little laser spot that tells you where you're measuring. There we are, 64, 65 in that liquid. Here. 1.4. It's actually nice water that's there. This thing will do up to 300 degrees. It'll actually measure a soldering iron tip as well. Although we have soldering iron thermistors and stuff for accurately measuring soldering equipment. But it's great for looking at heat sinks, cases, general equipment that you're about to use.
And it's useful to have one of these because you're better testing before touching. If you suspect, is that 7805 overheating? Yep, bulk chicken, yep, it's overheating. You might want to check with the thermometer first. Because if you look at the 7805 regulator or any regulator spec, it will tell you not to exceed certain temperatures without a heat sink or even with a heat sink, beyond which you'll either destroy it or, Chick was pointing out previously, gradually degrading the actual component. So it's worth checking. I'll be using that. I've got a problem with my 3D printer head, and we can check whether it's heating up properly using exactly that instrument. So that's before we even get to looking at tools themselves.
Yeah, these things cost about 20 or 30 pounds from our friends in the East. You can buy a proper one from Float or Radio Spares if you've got the extra money. And then there's the FLIR cameras for looking for Bigfoot and things like that. And they'll start at about 250, 300 pounds and go all the way to infinity. You can pay an awful lot of money for an infrared thermometer camera. But for a simple one spot reading, 20 quid gets you one of those, and it's quite a useful tool to have in your hand now.
So now we're happy we're safe to use our tools. The next time we have to make a connection. Before we look at actual individual instruments, we're going to connect the instrument obviously to a module to make the tests. So what do we use? What's the best things to use to make those connections? Well, clearly there's two things you normally do. You either have clips. Normally you clip that onto the 0 volts and then use the probes to test various parts of the module to get various voltage readings. And along the bottom here, we've got a selection of them. I'm not a fan of lots of long metal, lots of exposed metal when you're trying to poke around ICs and between tracks and so on. So the two on the right are the same probe. All I've done with that one is I've put some heat shrink over it so that only the tiniest bit is exposed. And if you minimize the danger of creating unintended shots when you're taking readings. For the same reason, you want to have a shrouded clip rather than an open one.
No.
And you'll see again, I've got shrouded connections here, and even shrouded get into the instrument itself.
Yeah. Those tweezer type probes I bought those for, I think it was about tenner for working on SMDs to replace a set that I had. The set that I had were made out of an old ISA networking card that I had cut up with a jeweler's saw and used the gold contacts at the end as tweezer ends. So I just cut basically a couple of strips off an ISA card and put a couple of pieces of packing between. And the fiberglass gave me enough flexibility that I could use them as tweezers and run a couple of wires back. And after I'd been using them for, I don't know, a year or more, I thought, you know, I use these sufficiently often that it's worth investing a few pounds to get myself a decent pair of tweezer clips. So those are available: Radio Spares, Rapid, Farnell, CPC, the usual suspects. That's what I mean. That's one of yours. Yeah. The red and wire, the red and black wires here are going on with tiny little micro grabber clips. These are pretty ubiquitous and again available from our friends in the east. It operates like a syringe at the back end. You squeeze the back with your thumb, with two fingers either side of the shaft of the thing, and two little wires come out, and when you release them, they close back in again. Dave, you got a bit, you can do that live just to see how it operates.
I thought this was just then.
All right, there we go. Now this is another system that is available, costs some money. We'll show you details of where and how to buy it if you're interested. It's more than the professional end. What we've got here is that piano paper is covering a metal plate. There's a steel plate in there. And these things are magnetic, and they pull down like that, and you put them underneath the board, pull them down, slide it in, release, and it holds the board steady. And then we have these guys to make connections. Now, at this point, I'm going to go. These, you've all seen Anglepoise lamps that are made of that flexible gooseneck material. These are Swiss made, and it's that flexible gooseneck material, except that it's made to a really high specification so that it doesn't flex left or right, it only flexes up or down. I'm going to put one in there. There's the flexible gooseneck material. Then at the end, it's got a great big weight, so that when you put it above something, the weight operates down and holds a little pogo pin, a sharpened pogo pin, and forces that thing to make the connection. Here comes another one. And you can simply put these things in and leave it connected, which means you've got two hands left to operate the oscilloscope or the meter or the power supply or whatever it is you're doing with it. You get a set of 4 of these, and they're simply electrical connections. You also get, you can buy others of them that are oscilloscope connections if you want to use an oscilloscope here. However, the actual thing itself, if I can turn it around about, you see the two big pins there, so you can connect anything there. If you want to connect it to an oscilloscope, all you need is a little jumper to connect it to a standard oscilloscope lead. So really the oscilloscope part of it isn't absolutely necessary. You connect that. And it's a thing that you have to actually use to see how useful it is. You just put it and take your hand away and it holds there. It's frankly amazing.
So instead of a third hand, it's a fourth, a fifth, a sixth hand, and so on. So you can take multiple readings at the same time while you're still twiddling knobs or volume controls and looking at the results.
Yeah, you can also put power in a certain circuit without putting the mains power on, sort of thing. Just flash up one chip and leave that power for you to do simple things.
And if you think that's really worthwhile, bear in mind that nothing is good necessarily comes cheap.
Half of me.
That's the current price. I just got off the internet yesterday. So we're talking 120 euros. What's that? It's almost the same in pounds, isn't it?
Almost now.
So it's not the cheapest thing, but you're doing lots of testing and you need lots of inputs and outputs to be tested at the same time. It's an ideal connection tool. Going down market, if you can't afford that, there's still all the clips that we looked at. So here's an example of a clip going on to pin 7 of a pick. Oh, it's upside down. Pin 3. Well,
Yeah,
there's a reason you came here.
putting the chips in upside down. That's one of your things, David. You shouldn't be doing that. You should learn not to do that.
I've got your Australia too often, that's not a problem. So
Pin 7 in Brisbane connection.
So once again, if you're trying to do other things and you're trying to hold your meter probe on that pin, it's going to slide off. You've all been there, it just slides off and the changes you'll short between pins. That particular clip is like a pincer. You pull back the body and it opens, you put it over the pin with the power off, of course, you release the body and it clips over the leg of the IC. And they come in all, let me just show it again. There it's there. As if you can just, you can just see opening and closing as I do it, can't you? Right. So you can clip onto a wire, you can clip onto a resistor lead, or you can clip onto the legs of an IC. The cheaper version of it is a simple hook that simply opens up, clicks over the wire. So that's handy for like testing wires on a layout, but wouldn't be so handy on electronic gear, whereas this loaded one is better. And like the clips that Chick was showing, once again, you can maybe just see it in there. You've got a connection you can take away to a meter or a scope or whatever you want to measure.
Standard DuPont.
That's just another variation on the same thing. Just push it and out comes the hook, let go and it clips it. Once again, to save you a third hand.
Another picture of one in use. This was from one of my previous presentations up at Shawlands. The point here being that there's a thing you can do with these. That was pin 3 of that chip, because I use the old standard,
UK orientation.
UK standard connection for pins. And pin 3 of that chip, I've actually put the chip back in the socket, but released pin 3, not put it into the socket, and put a probe onto it, so I can see what pin 3 is doing without it having any load, without it having any circuitry attached to it. Simply what would happen if I broke the circuit at pin 3 there and wanted to see what was coming out of that picture. And so that's what I did. I simply put the pin to one side and put one of these wee grabbers onto it, simply to let me see. And as you can see, there's a signal wire coming out the grabber, going back to my meter or scope or whatever it happens to be.
In that way, you're measuring on that pin without any effects of what would normally be connected to.
Pull up,
Pull it, change it.
Capacitance, load, and any of that stuff.
Right. And before we get, the last thing before we get to instruments is test the test leads. It may sound obvious, but we commonly get situations where either you've used jumpers or you've used the test leads themselves. You ever taken a voltage reading and it's not so good and you just turn the banana plug in your meter and it suddenly gets better with bad connections. So I've got here, that's two of them there.
Yeah.
I showed this at the basic electronics course using just the ordinary jumper leads with crop clips at either end, and to show that they're worth testing before you actually bring them into play. Go. So I've got two tester leads being the black there.
Two leads here, and what I'm going to do is I'll start with the green one, and I will simply measure the resistance that green test lead. 1.5 ohms. And we have a go with the black one. What the difference we had yesterday.
Also changed it to record them.
Ah,
Oh, there we go. Oh, in back and forward.
this black lead is kind of old and tired and a bit fusty and rusted and stuff, and we were getting double figures resistance off of it. Now, never try to demonstrate anything live. Maybe I warned you about that.
We'll just edit it out.
Aye,
No, the point about those test leads is that they're built down to a price, and they're just crimped inside. It's just a crimped connection, and over a period of time, the black one, if I took back the plastic sheath, you would find there's verdigris in there just over a period of time. And a couple of ohms didn't sound much, but the verdict there is, because you use Ohm's law, the more current you pass through one of these cables, the more voltage drop you'll get across it.
Furthermore, you'll have power loss. That power loss will exhibit as heat, and that heat will actually further degrade the connection.
Well, let's just take an example. Let's say you're passing, you want to use this to connect a local at 1 amp. 1 amp through 5 ohms is 5 volts. You wonder why your local is going very slow. It's nothing to do with the local, nothing to do with your power supply. It's to do with the quality of the leads you're using. And that applies for model railways for connections, but also applies to the test leads of the instruments themselves. So it makes sense, if you've got a multimeter, is to get the two probes, touch them together, and just check. Some you can center, some will auto center, so you're getting proper readings after that. But it's worth the effort. We're finally getting to instruments. When I say instruments, I'm using it in its broadest sense here. Let's start with the very simplest, which you've probably all used already, but it's still worth mentioning, I think. The old 12-volt card bulb trick. I've got it there in a couple of drop clips, but normally you may have that in much longer leads. And it's ideal for a model railway. You don't need to have a fancy voltmeter around for that. You just clip it onto one wire and clip it along other parts, and you'll soon find out if you've got a break. Say you're doing a break in a faulty fish plate or something, right? Or you're wiring up for the first time and you want to check that the block works. If that really operates, does that piece of track actually get power? If I throw that switch, does that bit of track get power? Well, you can simply test by putting the bulb across it, operate the relay, throw the switch and see it.
Because you're using a bulb that's got a significant power draw to light the bulb, you're passing significant current as well, so you know that it's going to work passing current to connection.
So we've got the little light bulb. Oh, we'll just have a quick look at chicks as well.
I never said
It's a Sunday as well. Right. Maybe a quick word about it.
Yeah, these are MES bulbs. You get standard Edison screw, which is the ones that you plug into the ceiling, and then you get small Edison screw, which are slightly smaller, and you get miniature Edison screw MES bulbs. These are MES bulbs, and these are actually baton holders. I've got two of these. I use them as test lights, mostly for the car, it has to be said. The test light for the car that I usually use, I didn't bring today because it's manky with grease for being underneath cars. One of them with the two black wires is simply a bi-directional bulb, and that'll light up as long as there's electricity there. And the other one has got a diode in series with it. I think it's a 5 amp diode in series with the bulb. And what that does is it turns that into a great big LED, so that I know that I can connect it one way around and it'll light up, and if I connect it the other way around, it doesn't light up. And so I can check polarity while I'm doing basic tests on 12 volts and 15 volts and 24 volt signals. Those are, I think, both 24 volt bulbs, because 12 volts will light a 24 volt bulb dimly. The 24 volt bulbs will light a 12 volt bulb very brightly, but for a very short time. So I always use a higher voltage bulb.
And you can imagine the benefit of those, especially if you're working under a layout, because you don't have to look at a meter to check what voltage is. It just either lights or not. Although it's not measuring the level of voltage, it's just detecting presence as opposed to amplitude. But nevertheless, very, very useful, I think. And then there's our good old friend, the track tester, which is just a step up from the chick's big light bulb, a LED bulb. This is two LEDs. You've all come across it. I think most of you have bought one. Most clubs have bought them. The difference between that and the other one is this one can test not just presence but polarity. If you put the tester on the track one way, the green light lights up. You put it the other way, the yellow lights up. If it's DCC, they'll both light up. So it's a very useful for a number of points of view. If you've got a layout that runs and doubles back in itself, there'll be times when the movement of the train is that way and then that way, but they're parallel. All you do is make sure they come across to see what light lights up, and you'll tell. And the other is when people are using mixed layouts, it's become quite common now for some parts to be DC and some parts to be DCC. It's a quick tester. Again, not telling you amplitude, telling you presence, but a step up from just a light bulb. And again, lastly on presence is the logic probe. The logic probe means what it says is it's designed not to measure current or resistance, purely measure, do you have 5 volts logic? Is it plus 5 volts or is it 0 volts? And you may say, well, I can do that just with my meter. And you can, but it can be awkward. Let me just show you the next one. Here's an example of the sequencer. Right? So if I put my meter onto output A, between there and 0 volts, and I then trigger the circuit, I can see whether it comes on. I can then do the same for C, D, and E. But let's assume for some reason the track is broken or there's a dry joint here. When you put your meter onto output B, it won't read plus 5, even though that may be switching to plus 5. So you can't tell a difference between an open circuit and it being at 0 volts level. And that's where the logic probe comes in. You put the logic probe, 2 wires across the power supply, and use the probe, and either one light lights up or the other. So you'll see it there. On the right hand side, you'll see that the red and black waves going to the power supply of the module you're testing, and the left hand side would go to an actual probe, and you can put it around various parts of the circuit and test that. They're genuinely getting 0 or 5. And if they don't light up, then either you're touching something that's not connected to anything, like a dry joint or a broken bit of track or whatever.
That's a pocket money kit.
That's the pocket money kit version. And kind of a price, pretty cheap. But to do stuff with logic circuits, it's worth it. And then there's this big boy, which is over here. Yeah.
Put that over there. Yeah, this one is the professional. It used to be you could buy these everywhere and anywhere, but I've noticed that recently they're becoming less and less available. That'll operate it'll operate 3 volts or 5 volts, right up to 12 volts. Quite happily, it'll give you highs and lows. It'll stretch the pulse so that if you get something producing a tiny narrow pulse, it'll stretch it before it puts it to the lead so that you can see that it's happening. And at the top end there, where it says CE near the bottom of the screen, you can see that it'll actually generate pulses. So for that sequencer, it would actually put in trigger pulses as well if you want. So it does a wee bit more, but not an awful lot more. I did a thing with students, oh God, too many years ago to talk about now, whereby I made a logic probe like that did produce pulses and measured them, and it used a single 7413 circuit, and it cost, including a piece of trunking, we used a bit of white conduit trunking to put it in, and I think the whole thing was built down to a price of £1.50 or something. So, you know, you really don't need to spend money on a big piece of equipment like that, because they're charging daft money for these now because they're so rare. So, I can't remember, but it's too much, basically. I'll have that one, so I wouldn't buy it again. But even if I didn't have one, I don't think I would buy one these days. The other thing is you can do it with an Arduino or a PIC chip. You can make a really good logic probe out a PIC chip and an Arduino and just do your own thing.
So up to now, everything we looked at has been relatively simple. And it just checks the presence or non-presence of a voltage or a pulse. Most of the time we'll be using these, checking for voltage levels, checking how much current a loco takes or a module takes, checking the voltage on the track, that kind of thing, checking resistance of wires and lengths of cable, lengths of track itself, and also doing continuity checks. We'll come to the more complex ones in a sec. But that's a very simple one for use on a layout, £2.47. Believe yeah, and that's including postage. Where it says track and track, those two red wires would want to be a lot longer, because then you can check, you know, from one piece of rail here, is it buzzing? Is it buzzing? Is it buzzing? Yes, buzz, buzz, buzz. No buzz. Oh, you've got a faulty fish plate there or something. So you can do very quick continuity checks, or you can put it on to a point. When you switch the point, does it switch polarity? So very cheap and very quick to use. Just got a PP3 battery on it, and again, we're testing for presence or non-presence. It wouldn't detect high resistance connections on a bit of track.
And again, very useful when you're underneath the board. Effing and jeffing and
nothing you need to actually look at. You just do it and see that you can hear it, it's working. And finally, we're getting to the position where we'll actually want to read real values as opposed to just the presence. Something you want to say, Chuck?
no, carry on.
Yeah. Hopefully by now we've all got multimeters. Over the last few years, I've been buying them very cheaply from eBay, although nowadays they're not so cheaply from eBay. We'll come to that in a minute. But compared to scientific instruments, they're still very cheap. They have to use batteries. Well, I don't need batteries because I'm picking up the voltage checks from whatever you're testing.
You only need a battery if you're measuring resistance, and that itself can be a problem. We'll talk about that as we go on.
The other big benefit is the next one for spotting trends. If I mention first of all how a digital meter works, digital meter is taking a reading and showing it on the screen as digits. Yep. Only problem is it can't do it constantly, otherwise the screen will be flickering the whole time trying to update it. So it does it periodically. It takes some samples and then tells you what the reading is, takes some more. So that's fine if you're trying to just read something that's not likely to change very much. What's the voltage coming out of that voltage regulator? But in model railways, it's very handy for spotting trends. So for example, you're measuring current as a local goes along, and it'll vary a bit obviously due to commutation, but if it's reading, and all of a sudden dips quickly, it almost certainly means you've come across a dirty bit of track. So that wouldn't necessarily show up in the digital meter because it may have happened during one of the updates. So for model railway uses, an analog meter can be very handy for spotting little transient changes that wouldn't be spotted by a digital one. The picture you see there is a typical analog one. It's got a needle that moves, and that's why you can check the flicker of the needle for variations, and it's got a scale on the needle as opposed to digital readout. The problem sometimes is one of parallax error. If you're driving along and your wife says, "You're speeding, you're doing 35, and you say, "No, I'm not." "Yes, you are." She's looking at it from the side, and she's seeing the needle beyond the 30, whereas you're looking at it as a driver, you're seeing it exactly at 30. So to get around that parallax error for analog meters, you'll see along the top here, it's a little mirror built in. And the idea is you take a reading, you look at the needle and its reflection until they line up, and that's you eliminating parallax error. And you get the most accurate reading you can get from an analog one.
The way they're manufactured is there's a jewel, like there used to be on watches, a jewel, the bearing, right at the centre where the needle comes into the centre of the scale there. And it is very delicate. All it needs is dropped once or hit hard to disturb that bearing, and the range can become a bit crunchy, and at that point you've basically got to throw the meter away and buy a new one because you can't fix them. And the other thing is, if you're measuring resistance, if you look at the very top scale there in that meter, the 100 ohms point is well over to the left, and then 50 ohms is a wee bit there, and then 30, and then 20 ohms is at the top. The further left you go, the lower the ohms is, but it's not a linear thing. From 20 to 33 ohms is the same as from 200 ohms to 20,000 ohms. So you can't say, oh, that's going up by a wee amount. The wee amount when you're at the one side of the scale isn't the same as a wee amount at the top end of the scale. So the resistance range is a bummer to use on one of these things. The other thing is that in order to get a resistance range at all, what it does is it takes the power from its battery and puts it out through the probes into your circuit. Now, if you've put a 9-volt battery in it, and then you try to measure resistance on a pick chip circuit that's got a 5-volt pick chip on it, what you're doing is you're plottering about your 5-volt pick chip circuit with a 9-volt battery. You can do damage, you can destroy things. So you have to be aware of the voltage that's inside an analog meter if you're using it in a resistance range. And then to further complicate matters, if you try to measure diodes with them, sometimes positive comes out the black lead, just to make things completely bloody mental. And except for modern ones, they fixed it, and in those, positive comes out the red lead. So sometimes positive comes out the black lead, sometimes positive comes out the red lead. You've got to be really, really careful. You have to spend time getting to know an instrument like that before you're going to be any good at using it, and before you're not going to have accidents with it. So please, by all means, treat yourself to one of these things, but be aware that there are things to be learned there.
If you can afford it, in other words, you're better to have both, I think. Now that's a particularly
Expensive.
complex and expensive one. The benefit of that there's a little people. When I first started selling these at the Sunday sessions, if I remember correctly, they were something like £1.50. You're lucky now you can get them in China for roughly £5. I think I'm going to show you later on. So they can be cheap. You get what you pay for. It's not a scientific instrument, that one, a fiver. But that's not the point. Most of the folk that are listening today aren't developing scientific instruments. They're just doing model railway work. It doesn't matter whether it's 12.1 volts or 12.05 volts or whatever. Really, the accuracy isn't absolutely essential for a lot of the stuff we do. But it does give you a big range of features. Some just, like that cheap one, just gives you the standard. It'll take voltage readings, both of AC and DC. It'll take resistance readings, it'll take current readings, and that's it. The more you pay, you can get to do other stuff. You can get it to do continuity testing, you can get transistor testers built in, and so on. There's a whole range, diode testers, all that kind of stuff can be built into it.
No. Just maybe confuse the need batteries. An analog meter, if you don't have a battery in an analog meter, you can still measure voltage or current with it. On a digital meter, if you don't have a battery, you can measure nothing. It just doesn't work. Without the battery, you're dead. Whereas the analog meter, you can still work most of the things you want to do without the battery.
There's one similar to the one I just showed you a moment ago, only it's got the upgrade. You can now also test transistors, but it costs you £7.50. And there's one slightly cheaper there. It's going to cost you roughly a fiver for the one on the right. And then there's a range of Chick's TARDIS objects.
The digital meters with a great big dial in the front. Behind the great big dial is a printed circuit board with lots of little sectors leading off to do all the switching. And it's very, very prone to oxidize and getting verdigris on it, and the switching stopping working. If you're going to repair one of these things, the first thing you'll do is take the cover off, take that big knob out, and take contact cleaner to the switching surfaces underneath there, because 5 times out of 10, that's the fault that's on it. And the better ones you'll notice they've got piano switches, or they've got something else, but they don't have that. They've got an enclosed switch, but they don't have that printed circuit board with the clicky thing on it. That's the kiss of death for multimeters.
So most of these we've looked at are ones for the workbench, but I bought this one, which I thought would be very useful. Because we can use it on layout. So let me just demonstrate that first of all. It's not cheap, but there it's there. It's the digital readout. It comes with a banana plug. It goes to a crock clip, sorry, to a probe rather. And I thought I don't want that because I then have to use 2 hands. So I've got a banana plug and I put a crock clip in the end. And that means I can do it one-handed. And I thought this is ideal for working under a baseboard, because you can do it one-handed. If I just switch on, there we go, and take a reading. That battery is a bit low, it's 8.83 volts, but the benefit of this, when you're working underneath, you don't have to even look at the meter. There's a hold the button in the middle. If I press that hold the button there, I can take it away. And that means I can put the meter, this probe rather, into all kind of awkward spots without actually looking at it. Take the reading just by pressing the hold and come back, and I can look at it. But that's very, very handy. You can line upside down under a layout to be able to take readings. It's also got, if I can get to work, there we go. It's also got its own little LED light, which again is very handy for working under a layout, because you can go straight to where you want without having to use a torch. So again, you can do it one-handed. For me, roughly £16. Keith got one very similar, which he paid a bit less for. But what's a very similar way, you can see that one's got a probe at the end. As you saw, I replaced that probe with a clip. But it does very similar. It actually does more functions. You can see it does capacitance and resistance. I've just showed you the DC. That's one they use most often, probably on under a layout.
Oh, talk about that fella. Yeah, there we go. Right. Now, I came across this guy this year. He was offered to me as a review piece. Did you review that for a well-known control engineering website? So I produced this in America. The basic course that you go on, the Logic 101 or Computing 101 or Electronics 101. 101 is always the first level course at university. And so this is the Fluke 101, which is their basic multimeter these days. Now, Fluke make a good multimeter, it has to be said. And this is just an excellent e-multimeter, with one minor exception. To give you the size of it, it's a little bigger than a cassette, about that size. It's built like a brick. It is dead strong. You can't flex it or do anything with it. It's 4 digits. It's 6,000 count, which means it's really quite accurate. But if you notice, there's only 2 probes, 2 holes in the bottom there, one for red wire, one for black wire. And the reason for that is there's no current measurement on it. It's very, very unusual to see a multimeter that doesn't measure current. Usually current and voltage are the first 2. But for reasons that I'll explain further down the road, I've got a better way of measuring current than breaking the circuit and putting a multimeter into the circuit to measure current. It measures DC voltage, AC voltage, millivolts, ohms, including continuity, and diodes. It'll also measure capacitance. Here's a new one. It will measure frequency. So currently it's picking up mains hum in the room. And if in the frequency, if I go to the other range on frequency, I get duty cycle. So I can measure PWM signals on DC. I've got a DC load, for example, a DC traction set up. I can actually put the crop clips in this onto the track, and it will measure the PWM percentage as I turn the controller up and down, which is very, very unusual in a multimeter. If I want to measure current, then all I have to do is put a 1 ohm resistor between the probes, because a 1 ohm resistor will drop 1 millivolt per milliamp or 1 volt per amp. So just by measuring the voltage across a 1 ohm resistor, I can measure milliamps or amps. But to be dead honest, it's not a thing that I need to do very often, simply because there's other ways of measuring current. And the fact that it doesn't have a current range isn't really, for me, a showstopper. The fact that it's a really, really good, really, really accurate, really, really versatile meter is much more important than the current range. When I did the review of this about a year ago now, it cost £35 to £40, It's went up significantly, like everything has in the past year. Since then, I think it's now 50 quid. There we go.
What's the current price, Ansel?
Current price, I will.
Oh,
Go ahead that.
got a shock there, didn't you? That's the as of yesterday. Right, Chick mentioned another way of measuring current without actually having to break the circuit, which is this unit here. So I'll put you straight back to Chick again.
And here we have Arduino and a 12 volt-ish supply to supply the Arduino. And I want to know what current's being drawn. So I'm going to put this boy into the picture and turn them on to the 2 amp range. And then I'm going to make it 2 amp DC range. And then I'm going to zero it. And now what I do is make the current start happening, and I simply loop this clamp over one of the wires, and it tells me that it's measuring 65 milliamps. Simply because there's 65 milliamps going through that black wire. Haven't had to break the circuit, haven't had to solder anything, haven't had to do anything. I simply hook the wire through that gap. And just for added grooviness, at the end of the range here, this one's got an NCV button, which is non-contact voltage. Remember the volt stick for detecting the mains? There's a volt stick for detecting the mains right at the tip of that clamp. So I can use it for measuring current. I can use it for measuring voltage. At this end here, whoops a daisy, there's a couple of standard banana plugs, and it's a voltmeter and a resistance meter and all these other things as well. So it's a standard multimeter, but it's got this clamp thing for measuring current, and the clamp thing for measuring current, for me, is much simpler. I'm going to disconnect it, put it on DC, zero it, measure the current. As that chip warms up, it draws less and less current. We've got a thermometer, we can work out how much it's warming up as well. My God, we could have planned this, David. We should have spent time in this instead of drinking it through the week. This would have been great. If you are looking to buy one of these, there are 2 or 3 different versions available. This one has a 2 amp, a 20 amp, and a 100 amp range. There are also ones that start at 20 amp and have a 20 amp, a 200 amp, and a 2000 amp range. That's weightlifting. Anything above 2 amps, I really don't want to know about. But then, depends what you're doing.
Now this boy.
All right.
First of all, the price and a quick description of what it can do up there.
These, again, this was another demo. I've had 2 or 3, I've been very lucky to get 2 or 3 of these reviews to do, because I keep my language much more temperate when I'm doing reviews than I do when I'm doing this thing on a Sunday afternoon. But these are made by the same people that make the TS100 soldering iron. Is it Miniware or Miniware they're called? And it's a fascinating little device. It's a tweezer again. There are 2 replaceable copper tips. The 2 legs of the tweezer are actually each a LiPo battery. And then the little bit at the head at the top contains all the multimeter functions, and it contains a lot of multimeter functions, but it's tiny. There's also a very clever arrangement at the where the 2 legs meet that involves magnets and stuff, rather than simply having a spring. So there's not a spring to wear out. Quite a fascinating piece of device. Now David puts his back over onto the camera. I'll see if I can get it glare free. There we are. There's a touch sensitive thing in the back here, and you can see I've got some SMDs underneath it. I'm going to zoom in on it and through just Spielberg mode. There we go. It'll measure capacitors, it'll measure resistors, it will measure inductors, it will measure voltages. It doesn't measure current. It will generate a sine wave, it will generate a noise wave. It's a fascinating wee tool. To give you an idea of the size of it, if I disconnect it from its power supply, go back into shot, that's a 3.5mm jack. There we go. Just to let you see the size of it compared to an SD card. It is a tiny wee thing, it'll go in your top pocket and it'll measure almost anything. It's not necessarily, because it's purely SMD, so it's not for general purpose use. But if you spend a lot of time looking around about SMD components, identifying SMD components, and try to work out voltages across SMD components and stuff, it's a wee bit of a lifesaver. What do you think?
And it's yours for only 65 quid, including free delivery.
Offer to review one and I'll send you one for nothing.
Now, what we've mentioned along the way, we've spoken about buzzers earlier on, the PP3 battery and just checking for continuity of track and so on. We thought it worth mentioning no way to use that on electronic equipment.
Yeah, I've kind of mentioned this earlier on in the presentation. If you have a continuity checking device, then before you use it in electronics, you should measure the voltage that comes out of it. That little float multimeter that I was ranting so eloquently about a minute ago, the voltage that comes out of that to check continuity is 0.2 of a volt. The voltage that comes out of my big float multimeter to check continuity is about 0.25 of a volt. The voltage that comes out of my AVO 8 is 15 volts. That'll destroy almost anything. So you have to be careful. If you're going to check continuity, you're going to do it in electronics, measure the voltage you're doing it with, which means you have to have another voltmeter to measure the voltage coming out of your multimeter. But then that's your problem, not mine. I've got multimeters coming out of my ears.
Right. If you've been to the 65 club, you've probably seen this demonstrated.
Yes.
But it's a very
been in my life, I've had to make cases for about 40 of these. If anybody asks me to make a case for one of these anymore, I say, oh, I'm out of plastic.
So let's have a look at one in action. You want to test whether something works. You also sometimes have components that the legend's been rubbed off and you're not sure what is this capacitance value or whatever. Then you can use one of these to quickly do it.
I have to say, I've got one of these on my bench, and every component that I pick up before it goes onto a circuit board gets tested, just to prove that I've got the right thing in my hand and I've got it the right way around.
So we'll just clip it into the zip socket, any component, press the button, checks the battery first, and then does the test. 1209 ohms, which isn't bad for a 1.2k resistor. Yeah. If I put in a little capacitor, do the same thing. Oh,
Pins running.
there we go. That's well out. That's meant to be 100 nanofarad. So it's not the greatest tolerance, 75 nanofarads. What else have we got? That's in properly. Let's see. Yep. It's spotted it's a diode. And gives some other information about it. What else we got? Oh, big Electrolytic will not work. Let's see. Yep, that's 100 microfarad capacitor. Test it.
Also worth adding that those little pads next to the zip socket where David's been jamming components in, you'll see there's pads on that board, and you can actually push SMD components on there to measure them.
Let's see if we can get a transistor on one of these. It'll work. I think you put in parallel, can't you?
I don't you set that up in one, a pin two, and a pin three.
Let's see if we can test it. There we go. Let's see what happens. Yep. It's found it's an NPN transistor.
Pin one's the collector, pin two is the base, pin three is the emitter, in case you've been wondering. B is beta, that's the gain of the transistor. So for every milliamp you put in the base, you get 420 milliamps in the collector. And the forward voltage between the base and emitter is 660 millivolts, which is about right.
Yeah. So we can check the quick. So we can quickly check what a value is and whether it's a working component.
Which pins which.
And orientation as well, which is great value for, I think, for the money. This is some examples. Don't you show them to your son already?
These are a much more professional, much more expensive version of it, made by a company in Derby called Peak Electronics. They tend to, they're actually, if you take the covers off, they've got pit chips inside. Some rather elderly pit chips, some of them. They have certain facilities that the cheap and cheerful Chinese one doesn't have, but I'm getting to the stage where I wouldn't like to live in the difference. The Atlas DCA Pro there, the DCA 75 at the bottom left, has got a USB socket on it, and it'll actually graph. If you put a transistor in it, it'll actually graph the characteristics of the transistor. So if you are making matched transistors for an audio output stage, or for an H-bridge or something, you want them to be exactly the same transistor, you can select them on that, whereas you couldn't probably do that with the £4 component checker. But this thing will cost you £75, so you probably, it's probably not worth it. I would, if anybody's interested, I would recommend getting the one to China first. It'll serve you very, very well. This is useful further down the road when you're doing much more complex electronics. But for just checking that if you're putting together MERD kits, and I have put together MERD kits using the Chinese component checker, and literally every component that I take off you know how they tape them together in the right order, even though they're taped together in the right order, I don't trust the elf. I pull it off, I put it in the Chinese checker and make sure it's the right component, it's marked properly, it's the right way around, and then I put it in the board and solder it. It's just, it's what I do. This is your hobby. You're supposed to be enjoying yourself. I actually enjoy, quite enjoy sitting doing that and spending time doing chronicle debris.
Now, we've been using or looking at meters to measure, but how do you measure something that's on the USB bus? The idea is that this gadget's got an input and an output. You can plug this end into a USB socket on your laptop or your computer, or you can plug it into a USB charger or whatever. And the other end you can take away to the device, tell you what the voltage is coming out of the laptop. So you can check whether your USB is working at its correct output voltage and the current that's been drawn. So let me just do a quick demo of that in action. Yeah, it's there. Power supply, ordinary charger, putting out 5.1 volts, no current because there's nothing attached to the other end. If I take my good friend again, the Arduino, plug it in. Taking 74, 75 milliamps. Yeah. So we can see what current's been drawn here, and we can check there's nothing here that's pulling down either this or your laptop's USB outlet, because you don't want to damage your USB outlets by going beyond the current that's meant to come from a USB 2 socket or a USB 3 socket. So it's a very useful little tool. You can also use it to check if you're charging up a device, because you'll see it at its highest current, dropping away till it gets to zero, and you know that gadget's then been charged.
I got one of these at the same time as Dave. It was myself that ordered them both to China, and Davey's still using his. Mine has been confiscated by a higher authority in our house. My wife noticed that if you plug it into the charger, you can see when your tablet is charged. So you don't have to open the tablet and look at it. So it now lives in our kitchen, and it's used by the boss for charging our tablet. I'm going to have to find myself another one.
You can buy ones that are actually a bit cheaper than that. That's got multi-functions. But if all you want to do is just measure the voltage and current, you can get them for about three or four pounds, something like that, roughly.
If you're looking for one of these online, look up UM24C. Right. The UM24 versus the UM24C. The C has got Bluetooth attached to it, so that you can read it remotely on your phone if that's what you want to do. No, me neither.
There we go. Oscilloscopes.
You were going to put that in. That is a Hartley 13A oscilloscope. I got one of those when I was 12. How sad am I? I've been about 1969 or 70. Ex-military, tropicalized, weighs a ton, and has 100 kilohertz bandwidth. I wish I still had it.
Apparently you can buy them smaller than that nowadays.
Yeah. Makes a great boat anchor.
We're not going to cover oscilloscopes in any great detail. It's a whole subject in itself. But we thought we'd quickly look at them.
There's that one, did you? Workhouse.
Oh, workhouse. Oh, right. The earliest ones, as you probably know, used cathode ray tubes. I used to have one that I built a kit from Heathkit, was it? Mm-hmm. Did a CRT version. Nowadays they're nearly all digital, or they work through your computer itself and use your computer screen. But the big analog ones, you can see all the pros and cons. They're given time. Probably not going to spend a lot of time on them.
No, there was an event about 5 or 6 years ago where one of the universities was giving away essentially oscilloscopes. They were giving away for very, very little money.
£30.
And a lot of NERD members bought these. They were Hameg 2-channel scopes. They've got a decent wee scope. And I did a thing up at Renfrew Model Railway Club demonstrating what you can and can't do with a scope and how to get the best out of it. And that's the classic analog oscilloscope. Great thing.
That's an example of a more modern version of the one you saw from Hartley.
You're not bringing that into my house. Look at the state here. Look at the colour of it. Mind you, it's heavy and it's not pretty.
This is more likely to come across now. And there's an example of one. A proper readout. Huge amount of functions and possibilities. And I've only read a fraction of the manual. So when you buy those big application packages and then they use about 10%, it's ideal to the oscilloscopes. They are really meant to be doing. You could do DC readings, of course, if you wanted to in the trace, but it's usually for recurring waveforms. But you can then capture a strip. So here's one that I showed fairly recently. I was using the scope to measure the pulse width modulation power to a motor. where the pulse width is wider and narrower, so it accelerates and decelerates. You can see it up there. As the pulse width is wider, it goes faster. As the pulse width is smaller, there's less power, it goes more slowly. So we can check both the quality of the output. We're getting a decent square waves that rounding off due to losses, and we're getting the range is fully widening, fully shortening that we'd expect. So we use it for testing the quality of the module you've just been working on. And that's when I did this yesterday to show a servo's output getting narrower and wider. It's a bit different because the map space ratio, that the space is usually always unchanging. It's only the width of the pulse that changes. And again, we can check that a nice clean square wave. And we can also use it to measure the frequency. If your scope supports it, it'll tell you right on the screen what the frequency is. If it doesn't support that, you can at least look along the scale and work out it took 10 milliseconds to get from a rising point to the next rising point, and that would work out as X hertz. So you can calculate it, or you can read it directly depending on what kind of scope you've got. Now, the other thing about it is that the two examples we showed you were dedicated scopes. You put it in a box and it did that one particular function, but there are ones where you can, like this one here, which is the one I've got.
Over here, we use it as a paperweight earlier.
This boy here, what you can't see at the other end of that picture is it's got a USB port. So you plug that into your computer, your laptop or your desktop, and it can handle two channels here.
Is oscilloscopio the Italian for oscilloscope?
Oscilloscopio. Never noticed that. It comes with a translation manual. So I've used this a lot when I was doing the basic electronics courses. So you can use it as an add-on. Instead of buying a complete scope, you can use it as an add-on to an existing computer setup. And I said earlier, the scope usually is for recurring waveforms. You're getting a sine wave, or you're getting a square wave pattern, or triangular pattern that keeps repeating itself. But you can use a mode to capture. And I was using this same module here, and that was me capturing a DCC signal. So you can see, once again, the quality and if there's any rounding off, and you can actually see the map space. And you can actually use that, we can translate that into what the command actually is in DCC. Well, that's us looking at, we're going to cover scopes any greater than that, just to say you can get analog, more likely nowadays you can get digital, or you can get add-ons in various formats like this to a computer.
If people wanted us to do a Sunday on oscilloscopes, and I'm sure we could either one of us do it or coerce somebody else into doing it.
Coercing people. Right. The
XML is like violence. If it doesn't work, just use more of it. Wave like you carry on. Do your work.
next thing is
Logic analyzers.
we saw earlier on the gadget where all the little pogo pins were on different parts of the circuit, and you can connect to multiple parts at the one time, and that allows you to look at readings at the same time. So you change one factor, what happens to all the rest? You can see it happening in real time, and again you can capture it if you want. The one I've got is the Sally, the one that Chip's got behind as a logic port. We'll look at them shortly. Yep, we'll come to that shortly. You could say, by the way, well, this one here, this has got two channels. I can measure two at the same time. Or if you've got a 4-channel version, you could just use a scope to do it. But what if you get 8 or or more that you want to be able to look at, well, let's look and see. There's 6 logic port.
That's there. That's 34 wires plus a central clock and grounds.
USB here.
You ever seen a cable that's USB A to USB A? Very, very rare thing to get. Aye. So you don't want to lose that. If you lose that, you're done.
Don't put it down anywhere.
Don't put it down anywhere. So these are made by a company called PCTestinstruments.com, and they cost a couple of £100 now. Inside it, all that's inside it is a large FPGA. An FPGA is a field programmable gate array. It's a chip that you can program to be whatever you want it to be. It's a 100-pin chip, and you can make it do whatever you want it to do. And it'll run at about 300 megahertz. So you can get about 100 megahertz out of that chip, out of that box, which is perfectly adequate for anything I'm doing with microprocessors, microcontrollers, low-end radios, even high-end radios. You can still use that on them as long as you use appropriate cleverness before you put it in.
That particular one can handle 32 readings at the same time.
34 readings at the same time. Huh?
Sorry, 34.
34. And it's a wonderful, wonderful tool.
I've got an example of that.
Yeah, that's there. That's an 8051 chip. 8051 is a 40, it was, they're redundant now. It's a 40-pin dual line chip with a glass lid that you UV arrays. That's how old it was. But if you look, you can see the individual data lines down the left-hand side, and above them the address lines AD70 and A15 to 8. And so the actual address lines, it's decoding those into the actual value of address in memory that it's currently looking at, and what it's seeing in terms of ones and zeros at those addresses are in the bottom lines. And up at the top, you can see the main crystal clock and the read and write signals going in as well. So that's really, really useful if you're analysing something that is complicated, something that's complex. It's beyond what we need to do for most of the stuff that we're doing in model railways, although I have to say I've had one out recently because I've been playing with this, the idea of sending back signals from a DCC decoder back to the DCC source in that gap. In order to get into that gap, you have to put a lot of data into a short space of time, and to capture it, you need something like this. So I've been playing with that. So yes, there are one or two people that might be interested in it, but for the vast majority of us, it's overkill.
That's a big 32 channel job. This is the one that I've got. It's only an 8 channel. But again, not cheap. That's 289, excluding that. They talk about 300 quid. And what you get for that size, that would sound like a lot for your money. It's an 8 channel version, complete with those same probes I was showing you earlier that are spring loaded. And
yeah, 100 megahertz.
It's what is it? Spec. Very similar kind of output. You can see here you can analyze I2C, SPI, CAN bus, and so on, various methods, simple parallel, and look at the outcomes. So it's quite complex, can do quite a bit for your money. So a lot costs a lot, it can do a lot. I was just thinking about that when I was I was talking earlier about Brendan's project, and it's using a 4017, which steps its way through each of the outputs and then goes back and steps through them again. And I thought, well, we could actually be able to do that. If we were to connect the logic analyzers connections to the various outputs and one to the clock pulse, you would see that every time the clock pulses, it moves on to the next output, and so on. And eventually, when it gets to the end, it does the whole 10, it'll change a pulse to the carry. You go to the next one if they require it. We could have used that to check whether, with a clean output, and in the order we expected. And last but not least,
Yeah, if you already own PIC Kit 2, PIC Kit 2 was the standard wee programmer for PIC chips for a lot of years. It was then superseded by the PIC Kit 3. But the PIC Kit 3 is actually a worse tool than the PIC Kit 2. And the difference between the two is basically the I/O on the PIC Kit 2 is completely available to you. So on the PIC Kit 2's program that comes with it, it opens up with that programming screen whereby you can see the data that you're programming and putting on the chip. But there's a tools menu there. And inside the tools menu is a UART menu. And the UART lets you use it as an FTDI chip for sending data to and from serial ports. And there's a logic tool in there as well. And the logic tool has got two modes. At the top right hand side of this, you'll see Logic I/O. If you click on that, then you get using the PIC Kit 2 to put ones and zeros into your circuit to test it. And then you click on Analyzer and you get this. Using the PIC Kit 2 as a very simple, is it 3 or 4 channel logic analyzer to let you analyze what signals are appearing in what order. And these don't have to be signals that are going into or out of the PIC Kit. You can use this to say, well, there's a signal arriving from the DCC input at the Schottky at the front end of my DCC decoder, and how long does it take before the DCC decoder sends a signal to the LED to turn it on? And you can measure that and things like that. You can do fairly basic but fairly useful logic analysis on a PIC Kit 2 with the software that came with a PIC Kit 2. If you've got a PIC Kit 2 lying about the house because you occasionally program PICs, then you've already got a wee simple logic analyzer to play with. There you have it.
so gents, we started off looking at a 12-volt bulb, which is cheap, and we've ended up looking at something that's useful, pretty useful, and free if you've got the PIC Kit 2. And that takes us to the end of the session. And I would open it up now to any questions,
Comments or suggestions from survivors.
and we'll cover it up so in case you make questions.
It's all right, kid on the mic's not working, baby. We'll be all right, would you?